kites and mono action. Yeah, before jumping into the topic right now, for a quick introduction, Telugu is one of the major Indian languages which has been spoken by 75 million plus speakers across the globe. Telugu, as most of our Indian languages, possesses a typical literary art form, which is the poetry. Similarly, Telugu language is also having the poetry. It is comprised of binary classification system with some language specific constraints. Yeah, this is the graph that I have considered from Indian Census 2011 regarding Telugu people. Yeah, let us discuss on different terminologies. Yeah, I think every one of us belongs to different parts of India and different parts across the globe. Yeah, here the first basic unit in Telugu language is the character token, which could be assumed as human perceivable character. We can correspond this character token to alphabet in English. In English, we are having alphabets. Similarly, in Telugu, we are having this Aksharamala, we generally call. We can correspond to this character token. Yeah, every character token in Telugu could be classified with respect to the pronunciation, especially how light the syllable is getting pronounced or how heavy the syllable is getting pronounced. If the particular syllable is pronounced light, then it is generally called as Laghu. It is represented with the letter I. If it is pronounced heavily, that is some broad elongated pronunciation is there, it will be represented using the symbol Guru, that is the U. After syllabic classification, we are having syllabic sequences where group of syllables form together to be called as syllabic sequences. In syllabic sequences, we are having different types. That is, 2 syllables can form a syllabic sequence, 3 syllables can form a syllabic sequence, and 4 syllables can form a syllabic sequence. Each of these combinations, permutations, and combinations are having predefined names in this language. If we observe 3 heavyweight characters, then the particular syllabic sequence is termed to be as Ma. If we observe 3 lightweight characters, lightweight syllables, it will be considered as Na. Similarly, we are having all the predefined types for 2 syllabic sequences, 3 syllabic sequences, and 4 syllabic sequences. Moving forward, when we are exploring the code, we can easily understand. After syllabic sequences, we are having poem. Generally, this poem, there are different types of poems. Each name corresponds to each type of poem. Just like if we deal with some classifier models, we are having different classes. Similarly, each name corresponds to each type of poem, where each poem is having particular predefined syllabic sequence and also some language-based constraints. After poem, we are having Satakam. Sata means the 100. 100 similar poems combined to form the Satakam. Yeah, if we try to summarize the entire slide, we are having first some basic unit, that is the alphabet, which is character token. Again, the character token is classified into either lightweight or heavyweight. Group of lightweight and heavyweight together form syllabic sequences. Syllabic sequences with some language-based constraints form poems. 100 such poems form Satakam. I think everyone got it. Yeah, let us do some hands-on. This is a word in Telugu language which corresponds to elephant, Enugu, Enugu. Here, the first letter A is a heavyweight and it is pronunciated a little bit elongated when compared to Nu and Gu. So, the first A is classified as heavyweight and remaining 2 are classified as lightweight. When we observe, we are having U, I, I. The predefined syllabic sequence name for U, I is Bha. Similar syllabic sequences I have given here. Similar syllabic sequences with some predefined constraints, which can include caesura, alliteration pattern, etc., and also a number of tokens in a particular line. The number of lines in a poem together forms the poem. First, we are having we are taking input of Telugu text. Later we are classifying with respect to each syllable, and we are forming syllabic sequence. Syllabic sequences form poems. Yeah, the major challenge before starting our work, the major challenge that we have faced is there does not exist any data set for this Telugu metrical poetry, and also no Python based computational framework which is openly available. So we try to build a data comprehensive data set as well as computational framework. Yeah, in this work, what we have addressed are the data. First, primarily is the data. As we previously observed, we are having some tokens, that is characters. Each character is again classified into lightweight or heavyweight based on the syllabic pronunciation. Such annotated data set does not exist. So we annotated the data, we prepared the data, and we published it on open source CC by 4.0 license, and also the computational framework, the comprehensive computational framework to classify whether given character into lightweight or heavyweight. Again, the group of syllables into sequences and poems. The computation framework we have made. In this process, we have introduced the prosodic tokenizer as well. This tokenizer can be used to extract character prosody-aware characters in Telugu language, which could be even extended to other languages as well, and also the evaluation metrics to evaluate the performance or to quantify how accurate the given poem is. Yeah, regarding the impact and community value, we have focused on majorly four different areas. One is the data and knowledge democratization. Before starting our work, I have gone through several websites. However, the data and the annotated Lagu Guru sequences are not available. So we have spent almost 3 months annotating the datasets, collecting the datasets, annotating the datasets by hand, and then verifying. So we wanted to democratize the knowledge and the data as well, and the algorithm framework, and we have created and we have published in Python as a Python library, as well as it leads to endangered traditions preservation, and also this framework can be extended to other languages as well, other low resource languages where poetry exists. We can mm, develop poetical frameworks to those languages by using this competition architecture, so that it enables global research and collaboration. Yeah. To summarize, I will be discussing on the list of terms so that we'll be on the same page. Here, the aksharam means the token, the human perceivable character token. Most of the times, I will be using English, English words so that everyone can pick up. Yeah, but for our more understanding, I have added. Yeah, Lahu means the lightweight syllable. Guru means the heavyweight syllable. Poem means Padyam means the poem. Vruttamu Jati Upajati means different classes of poems. Generally, we are having different classes of poems. Inside each class, will be again they are separated or classified into different types like Kandamu, Champakamala, Uppalamala, etc. Shatakamu means the collection of 100 poems. Yeah, regarding the data set, we found one website. Let me show it. Yeah, this is the website that we have found online. This website is andhrabharati.com. Yeah, we are thankful for this Vadapalli Shesh Talpasai and Kalpanaga Bhushan Rao for maintaining this website. Here we found multiple Telugu literary works. However, these are only poems. These are on Telugu language. We will be exploring the transliteration versions as well little later. Yeah, here we can find the type as well as the Telugu texts. In this work, we have scraped all these things and we annotated the dataset based on the syllables. That is, broadly, we found three different classes in combinedly 8 types, which led to 28 different satakams. Satakam means 100 poems. Some satakams may contain more than 100 poems, like 200 poems or 1000 poems as well. Yeah, a total of 4651 poems we got it, which led to the total number of tokens to 3 lakh plus. Yeah, and this is the computational architecture. that we have focused, it majorly comprises of four different modules. One is the syllabic module, which classifies the given character into heavyweight or lightweight. This is the constraint module. This module actually implements language-based constraints. This is the poem configuration module. As we previously discussed, each poem is having some language-based constraints as well as the syllabic constraints. This can be used to configure each poem so that the predefined configurations could be used in scoring module. This scoring module is an aggregator module. It acts like an aggregator which takes input from syllabic module, that is the light versus heavy classified tokens and language constraints, as well as the poem configurations. It implements the scoring and computes the scores in 0 to 100 range. Yeah, we'll be exploring each module in depth. Yeah. Yeah, coming to the first module, syllabic module. Here the syllabic module takes input text, whatever be the text that is given, it takes input. Yeah, here we defined two major methods. One is for the prosodic tokenization, and another is the syllabic weight classification. Yeah, here this is the class that we have defined. Inside the tokenized method, I think everyone is aware of regular expressions, Python regex module. Using the regex module, we are able to split the given text into Unicode graphing clusters. During our work, we found like there exist some limitations in regex as well, because it is implementing some tokenization. However, the output tokens are not exactly corresponding to the tokens that generally Telugu human perceivable characters are not matching. Yeah, we'll be exploring whenever we are going through the code. Yeah, after then we removed any unwanted characters. We have written a loop for loop to iterate through each character, and we implemented language-based constraints. There exist some constraints to identify the given input as a character or not. We implemented those, and we are able to tokenize. This is about prosodic tokenization. Coming to syllabic weight classification, after the output of prosodic tokenization is consumed to generate the syllabic weight. Here we have written the language-based linguistic constraints to determine whether the given token, that is character, as heavyweight or lightweight. Yeah, to implement this, we have prepared a Nidhi. Nidhi means the alphabet database. Here we have defined all the Telugu alphabets, categories of alphabets. Like in alphabets, again, we are having vowels, consonants, and vowel killers, like that. And also the predefined syllabic weight classification for vowels. Let me go into the code base. Yeah. This is the Nidhi module. Here we have defined different lists where each list corresponds to each class. This Varnamala represents alphabets, and also this Achulu represents the vowels, list of vowels, and Hallulu, this represents the consonants. Yeah, yeah, these are the different classes. Yeah, this is the Lagu Guru map. This is the syllabic classification map, where each character token corresponds to either whether it is heavyweight or lightweight. Yeah, and generally the major challenge in Telugu language is here we are having around 50 plus alphabets, 50 plus character units. However, in reality, when we are talking or when we are writing, these consonants and these vowels together combinedly form new type of human perceivable character units, which is a bit challenging to deal with. Yeah, we have implemented the algorithms in such a way that it can handle complex orthographic clusters and vowel killers. Yeah, as well. This Nidhi we have consumed into this check Laksham. Yeah, here it implements the syllabic classification as well as the tokenization. Sorry. Yeah, this is the thing. Lagu Guru. Here it implements the Aksharam tokenizer. We have named as Aksharam tokenizer. It consumes input text. And then, yeah, here we have used regular expression to split. We have removed any unwanted characters. Yeah, we have written some for loop to iterate through all the extracted characters and implement the tokenization. And then we have used the Nidhi previously here. we have defined some predefined Lagu Guru sequences, that is the heavy versus lightweight. Here we have iterated through each of the generated token and classified accordingly. Here we have defined some Telugu language specific rules as well regarding vowel killers and complex orthographic clusters. Coming to the second module. Yeah, coming to the second module, this is the poem configuration module. As we previously discussed, we will be having one characters. Each character can be classified into either heavyweight or lightweight, which we have discussed a little bit earlier today. And then the group of syllabic syllables combined together to form the syllabic sequence, and we'll be having some syllabic set of predefined syllabic sequences with language based constraints, yeah, together form the poem. This poem configuration module acts as a configurator, configuration, predefined configuration to check the given poem. Yeah, here we consume the input from Ganam. Here inside the Ganam file, we have defined the syllabic sequences data from syllabic sequence to Ganam name, as that is the syllabic sequence name, as well as the name to syllabic sequence. Code. Yeah, this is the Ganam file. Here we are having predefined, as we previously discussed, like the syllabic sequences may contain single syllable or set of two syllables or set of three syllables or sometimes set of four syllables. These are having predefined names, predefined classes, which we have written here. We have utilized this predefined syllabic sequences into this poem configuration module. Here, each poem, if we take an example of Kandam poem, this is a class. Yeah, for now, let us call it as K. Yeah, for this K poem, we'll be having n padalu. That is, number of lines could be number of lines should be the four, and also the ganakram which corresponds to these syllabic sequences, they should follow this odd and even, etc. And also the etistano, this corresponds to the alliteration, sorry, the caesura, which acts as halt position. Yeah, in every given line, the first element should possess that is the caesura with the second element we have defined. Yeah, these are all some other metrics, some other linguistic constraints. Yeah, I think possesses its own linguistic constraints. Such constraints could be included in this configuration module, where all the predefined configurations exist. Later, the next module is the constraint module. This constraint module, we have included all the language-based constraints. Apart from the syllabic sequences and poem configurations, we'll be having other constraints like caesura and alliteration patterns as well. In this constraint module, we have written this caesura check and alliteration checks. Yeah, for this thing, we have defined, generally we use the utilities function. Here we named as Panimuttu, synchronizing Telugu language. Inside this Panimuttu general, this is the utility module. Here we have defined general purpose utility functions to handle vowel diacritics and vowel lengths like that. And it takes input from Nidhi, that is the alphabet data that we previously gone through, and also the syllabic sequence data, predefined syllabic sequence data, and it checks the given constraints. Let me go through it at a glance. Yeah, this is the check. Yeah, this is the check yeti. This actually checks the caesura of the given line. It takes two inputs. One is the two inputs. It checks whether the two elements or character set, the given two indices, are possessing or following the caesura or not. This caesura is also predefined for simple vowels and consonants. However, coming to the complex orthographic clusters, vowel killers, and complex conjugates like that, we need to extract. We have implemented here. Yeah, we have iterated. Basically, this implementation majorly focused on iteration. We have implemented this using a for loops and iterations. Yeah, this could be optimized. Now let me go into the next module. This is the scoring module, which acts like an aggregator for all these things. Yeah. To summarize, we consider input text. We have gone through the syllabic module, which classifies the given text into light versus heavy, and the poem configuration module, where we have set all the predefined configuration for the poem, and the constraint module, where we have defined other constraints apart from syllabic sequences like caesura and alliteration checks. Yeah, inside the scoring module, we implemented for loop where we iterate through each character token, and it consumes the current padyam type and assigns the syllable sequence name, and it tries to compute the score. Here, we have defined the scores in five different dimensions, and later we aggregated it using weighted average. Yeah, calculate and also calculate constraint specific scores as defined in the poem configuration module, and aggregate all the micro scores into a single score using the arithmetic average. In the recent versions, last week we have introduced the weighted average. Let me go into it. Padyam here. Yeah, this is the check padyam. Here we are trying to aggregate from different modules. Yeah, these are the different scores. Let me scroll down. Yeah, these are the different granular scores to determine whether it is a padyam, as we previously discussed. Um, each poem will be considering of different constraints, which includes a number of characters and as well as the syllabic sequence, the caesura pattern, which is nothing but the etisthanam, and also the number of characters in aksharalu, like that. Later we have and also the prasa alliteration pattern. Yeah, by using these weights, we have implemented this weighted average sigma fi xi by sigma fi. Yeah. Also, we are outputting chandas score, that is the overall average, as well as the micro score. Yeah. This is about architecture. Let me summarize what we have discussed so that we can get bigger picture. We are getting input text. Later we are having syllabic module, which actually splits the given text into character tokens. Later the character token is classified into whether lightweight or heavyweight. This constraint module implements the language-based constraints such as caesura and alliteration patterns. This poem configuration module could be used to predefine the given poem types. Actually, these poem types may be different from each language to each language. And the scoring module aggregates all these things and computes the score, and it outputs the average. Yeah, the proposed framework solves prosodic tokenization, syllabic weight classification, and also mathematical numerical evaluation of poem in Telugu language. Here we have handled all the vowels, consonants, vowel diacritics, vowel killers, nasal sounds, complex orthographic clusters as well. All these things. Yeah, coming to the benchmarking reports, that as we previously gone through the slide where we have.
Hi, Sri. Sorry to interrupt. It's just that
Okay.
you have about 3 minutes left. So just thought I'd
Okay.
let you
Cool.
know.
Yeah. Yeah. Cool. Cool. I will spread. This is the benchmarking score that we have achieved 91.73%. Yeah, also we have published a open source Python library for this. We can install it using pip install chandasu. It is available on SciPy. Also, we have published our preprint on RxIV. These are all the different websites you can access. Yeah, coming to the optimization of the existing library. Basically, this existing library is based on text processing. Yeah, in future we are trying to integrate numpy, scipy, and spaCy tokenizers as well to convert the existing text based processing into numerical processing. and this matplotlib and seaborn to create some intuitive visualizations to uncover the underlying patterns. Yeah, what's our next step could be the dataset expansion, expanding the dataset and also including more type of poems. The current implementation lacks handling sandhi rules. Generally, different sounds combine to form different another new type of sound. That thing we need to implement using. We're planning to build a model for this. Yeah, also expansion to other languages where metrical poetry exists. Finally, context. Assume user gives some context. Automatically, poem will be generated using some LLM or small language. Yeah, I look forward to possible collaborations with the community for this. Yeah, thank you. Let me go through a quick demo. Here I have hosted on Hugging Face. Yeah, this is the space. It will take some time. Yeah, this is the input area. We can pass some Telugu text here, and if we click, we can select the uh, type of. Here we have provided different types of poems. We can select what could be the type, and if we click on analyze, it computes the score. Here, this poem is correctly matching with all the metrical properties that like number of lines, syllabic sequences, number of character tokens, and alliteration. Yeah, these are the tokens as well as the corresponding syllable sounds. Yeah, if we remove some text here, it may not be satisfying 100% because the number of syllables may be different, and also the number of characters. The predefined padyam possesses will be reduced, so it output a lesser score when compared to the previous. Yeah, this is what I meant. Any queries we can discuss?
I don't see any questions so far in the chat, but in case you do have, in case the folks here do have any questions, feel free to reach out to him. I think he has posted his socials on the GitHub issue thread and even in general. So yes. With that said, I
Yeah,
think I'll hand it over to Pranav. Oh, sorry, Kia.
yeah, yeah.
Yes, question.
Yeah,
Actually, I
sorry to
do
interrupt.
have one question. So,
Yeah,
is there like a competition? So, like my question is uh, not from a scientific perspective or anything. It's more from the perspective of someone who reads poetry a lot. And for English poetry, the most common meter for poetry is iambic pentameter. Uh, Came up in the 14th 15th century, something like that. So is there a computational framework or like some sort of similarity in Telugu poems? Like what sort of meters do Telugu poems follow, and like what's the most common meter?
yeah. The most common matter could be the Theatre Giti. Here we are having the name a bit different. It is Theatre Giti. Um, yeah, other meters include the Champakamala, Utpalamala, like that. It has many similarities with the meter that you have mentioned. Like it is also based on the pronunciation. If the syllable is pronounced lightly, it can be classified into lagu. If it is pronounced as heavy, it will be classified as guru. That is the u. Yeah, some based on the linguistic constraints. Again, that poem types are present. Yeah, to answer your question. The theatre Giti is one of the most famous things in Telugu. And also people frequently use Utpalamala, Tampakamala.
Got it. Thanks, Ray.
Yeah, yeah. Also, thank you for this opportunity to present Chandasu. Special thanks to SciPy team for organizing this platform and also thoughtful insights in preparing the presentation.
Thanks, Reha. That means a lot. And thanks for also taking the initiative to submit a proposal. It does take a while, so thank you for following it through. With that said, yes, I'd like to call upon Pranav to present on the next topic. Something I'm looking forward to. Yes.
Hey, hi. First of all, really amazing talks by Sadhna Abel and Badhushi Pawan, really inspiring. And again, thanks to Srihari, Agriya, and Aditi for organizing this. I really appreciate your time and energy. So I am Pranav. I am creator and maintainer of Ramanujan language and platform. So it's a new way of seeing how we can do computation. So I'll be presenting that. I'll just share my screen. Yeah, can you see my screen?
Not yet. It's not. Okay.
I think it's visible now, right?
Yes, it's visible now. Yes.
Okay. So, what's the inspiration here? So, in 1969, we were able to land on moon, and the computer which helped us do that was called as Apollo guidance computer, and its computation power was equivalent to today's scientific calculator compute power. And these days, we have mobile phones which have at least million times more compute power than that computer, and we have billions of such devices, and most of the time they are idle, they just don't do nothing. So the thought is, why not use the compute power of such idle devices? uh, but we there is this thing called Boink. There is this project run by Berkeley, so it's also on same principle, where people can donate their computation power. But the problem is that for a new kind of simulation to run on Boink, the person who wants to get their simulation run, they have to write new binaries for all kind of devices that they want their simulation to run. So if I want to run a new kind of simulation, I would have to write a new binary, compile it, distribute it, and also the devices which want to contribute to that computation, they have to download and install that. So that's where the difference comes in Ramanujan. So the idea is that we have just one interpreter, that's a binary, and that interpreter is going to be installed on all the relevant devices which can donate their compute power. And any simulation which anyone submits, that gets translated to uh, some bytecode which is understood by this interpreter, and that bytecode comes to the device, and this interpreter runs on that and it returns back. So here we are empowering users to get the simulation run without the hassle of writing new binary and getting that binary installed on those devices. Now, some performance stats for the interpreter. So this interpreter is written in C++. Right now, it has limited features. So it has all the relevant features which are required for basic programming, that are loops, functions, variable array length, arrays, uh, all the basic functionalities there. And right now it is 17% faster than CPython. CPython is the original interpreter for Python language, which is written in C. And if I compare it to MATLAB, so I had compared with the Octave distribution, so it is more than 20x faster than that. Actually, MATLAB is far slower. So just wanted to put a point here. Now, a story behind this performance increase. So, initial interpreter was written in Java. So the thought was that, hey, Java can be run anywhere on just that device has to have that JVM to run that. So I wrote an interpreter on that, and it was slower. So for example, if CPython was running at 400 millisecond, it was taking 8 seconds. But I was fine. Okay, the computation is to be distributed around devices, and it can be asynchronous, and that should be fine. But I tested with an Android phone. I found that it took 2 minutes to run same simulation, although the CPU power of that phone was equivalent to PC on which I was running my simulation before. So I thought, okay, now 8 second. It was already 8 seconds, so I thought let's um, improve the performance first. So I started going through Jython. So Jython is it's a very old project, and I think it's out of maintenance now. But the idea was that we can run Python program in Java. So that's why it was called as Jython, J for Java. So I took lots of inspiration from there, and I reduced my 8-second performance to 700 millisecond performance on MacBook. But it was still running 30 seconds on Android. And the reason is that there is this called Android runtime, and it throttles a lot of Java code. And probably that's the reason why most of the high performing games in phones are written in native. So that's where I thought, okay, Java is not going to be good. So I converted my interpreter to C++. And now, because Jython was already kind of a copy of CPython, it had the main logics were similar in CPython and JPython. So I already had a lot of optimizations in my code. It was still comparable, or still much, not much, but still slightly more than this CPython. So I started to do lots of optimization. They were required, and the result of those optimization was that Ramanujan right now the interpreter is 17% faster than CPython. Now, what just an overview on what additional optimization led to this 17% increase. So there are three things which people should know. That's why I'm sharing here. One is that one should reduce pointer hops. As low pointer hops, that's the best. Um, Reduce number of function calls even on the same object. Uh, so there is the symbol translation that happens on function call, and reducing number of function calls will improve the performance of the code. And also we should minimize new object creation and destruction, and to the point of that, even to the objects which are getting created on a stack. So I'm not going through that malloc thing or new thing, but even if I'm just creating a new object on a stack, that's a performance hit, because constructor is getting called, and when a stack will pop, the object will be destructed, and that's an additional performance skill. So one thing which helped in my journey was flame graphs. It helped me analyze a lot in my code where the bottlenecks are, and what is causing some problem and so on. So just an example I wanted to share. So on the right side I have a snippet, and here I am having a double field, a variable which I am creating on a stack. Okay, and with this particular function was taking 4.5% of total runtime of a run, right? And when I remove this stack variable, and I use a field variable, this 4.5 percent of the run gets shortened to 3.9. And also one thing, the caller, which was this function command RE, that was taking 32.1%, it also reduced to 28.6%. So all in all, flame graphs are best friends for C++ program. Now, how different is Ramanujan interpreter from CPython? So CPython maintains something called as frame object, and that contains all local. So frame object is nothing but an encapsulation which has all local variables and global variables, and each bytecode element has index to that index in that frame object. So if it has to call the 0th element of that frame index or frame object, or any index, so that's how CPython works. But in comparison, so in Ramanujan, each bytecode element gets converted to a memory object. So I have an object for operation, I have an object for function, and this creation of object is just one time thing, which is kind of a warm up, and I do include that when I'm doing the perf comparison. So that this warm up is also part when I say that it's 17% faster. Uh, and when my operation is executed in Ramanujan, it knows what memory objects to work with, and so this reduces my repeated pointer memory hops that would have happened if someone goes with the frame object approach. Now, parallelism across machine over Ramanujan platform. So through code, you can define how you want the parallelism to run. So right now, on a given device, parallelism is not allowed. I mean, it can run, but when I so some not multi-threaded in one process is not allowed right now. Although I have that in my future goals. But I can have parallelism across devices, and I can break my program and distribute it among different devices just from code. I have that control. So, for example, if I talk about this DAG, right? So it starts from and 0. Then there are two parallelism which happen T1 and T2. And when both uh, computation are over, I want to coalesce that and run N1. And then again, I want to do some parallel computation T3 and T4, and then finally coalesce that in N2. So this is how. In Ramanujan, you have two methods: thread start and thread on end. And what thread start means is that here distribute it to some other device or distribute it among the devices. And so this is how it's written in Ramanujan on how to distribute the code. Now some demo. Okay. So for this demo, what I'll be doing is that I have a linear regression program in Python as well as in my language. So the idea here is that I'm kind of doing the Celsius to Fahrenheit conversion. Now, if I run on Python, it takes about 4.3 seconds, and now I'll run on my language on my interpreter, and so there is a difference. So it took 4.3 seconds and it took only 4 seconds. And then once my code is over, I can start taking out the data. For example, there was one variable called as answer x1, so it gave the value of one variable. Similarly, I had this answer y1, it will give me a different value for that. So yeah, so this is how it's run. And also there is one portal. um, uh, okay, so there is this optimization algorithm called as whale optimization algorithm. It's so the author of that algorithm mostly writes in MATLAB. So I just took their code and I converted that to my language code. And we can do this distributed computation over this portal, which you can go to portal.ramanujan.dev, and there you can submit a job. And after submitting, after some time, when the computation is done, you will get the data out in a tabular form. uh, uh, and yeah, now coming to architecture. So there are two things to talk in the architecture. One is the backend service thing and how this asynchronous flow happens, and the interpreter, which is more important. So if I talk about the backend service, so what happens is my dev console. So there is this service called as middleware. It's nothing but it just can translate my code to that intermediate code. So I'll send a request to middleware. It will convert the code and it will send back an async ID. And the idea is that now middleware once translated my code, now it will do the orchestration in the backend. And to my dev console, the thing which my dev console has is the async ID. And now dev console will be polling to middleware and keep asking, hey, is this async ID done or not? And that's all for dev console and middleware. Now going much beneath into the backend services. Now there are three services actually internally. One is middleware, one is orchestration, and one is Kafka Manager. Now middleware takes care of just converting the code, and now when it converts the code, it creates a DAG of computation. Okay, so uh, something like this gets created in middleware. So it creates a DAG of the code, and it's just controlled through the code how you write thread start and thread on end, and result of that your this middleware service will create DAG for that. And now, so on a DAG, there will be a head node, right? And that head node will have children, and then the graph will become bigger, and in the end, it will coalesce to one node. So, what middleware will do is from that DAG, it will take the head, okay, and it will call the orchestrator. And then orchestrator also do the same thing. It will create an async ID and it will give back to middleware. But now middleware pushes this orchestrator async ID to Kafka Manager. And now the communication between middleware and orchestrator is done. And now orchestrator will be starting to contact devices, and it will start orchestrating how a particular computation node in that DAG has to be computed. And orchestrator will take care of that with the devices, with any kind of device. And now, what's the use of this Kafka Manager? So what Kafka Manager will do is, so it's a kind of pub sub service. So Kafka Manager is kind of misnomer. You can have any kind of pub sub here. You can have Kafka, or you can have pub sub, or any implementation. So when middleware had got async ID from orchestrator, it published an async ID into the Kafka Manager pub subsystem. And when now Kafka Manager keeps polling the messages which are published onto the queue, and when it will take out that message, it will have that async ID, orchestrator async ID, and it will Kafka Manager will contact middleware, and then middleware will contact orchestrator asking, hey, what's the status of that orchestrator async ID? And if orchestrator gives back, hey, that computation was successful, then middleware will get the data from orchestrator, and now it will decide how to go forward. Now it has the memory, it has the knowledge of how DAG looks, and it will see what are the child nodes of that, and it will do the same thing for all the child nodes. It will call orchestrator, and that same flow happens. But there would be some nodes which would be waiting for parent nodes to complete, right? And let's say one of the parent node completes, and the other parent node is still in work in progress. So middleware has that understanding that, hey, it has to wait for the other parent node also to complete. And once that happens, when all parent nodes for a given child node are complete, it will call for the child node, and so on. It will compute, it will orchestrate the whole DAG. uh, Now there is this pseudocode for DAG computation which is given. It's on the Ramanujan GitHub page. uh, yeah. And now coming to the bigger thing, which is the interpreter, how interpreter works. uh, so the interface to my interpreter is processor, okay? And this processor will get the bytecode or the intermediate code, and it will translate all those bytecodes into the memory objects, and it will create a map of that, okay? And when it's creating map of that, I mean, when it's converting a given bytecode to a memory object, it doesn't know, for example, if I talk about if condition, right? So there is a jump, and on jump there would be a sequence number it wants to go to, but when it's converting for that if condition, it doesn't know what is there on that sequence number. So that's what my fixed graph helps in. And once I have created all the objects in memory, now I call fixed graph, and that ensures that for a given node, it understands what all are the nodes or bytecode objects which it can contact to. Then, uh, yeah, then the thing starts. Hmm. So it's a very simple thing actually. So what happens is in so all the bytecode objects are called as command RE, and on my processor there is a while loop, and all the commands get executed. And uh, when it called get on any command, then it has to demarcate there that hey, if it's for if, or if it's for function call, or for it's and for operation. And that, so kind of it's kind of polymorphism that happens. All the objects, let it be for if, for function, they have their own implementation. And for my processor, which is the interface, it just knows that it's command, and it keeps on calling dot get, I mean the get method on those object. And so for if, it does like it does the condition check, then it says that okay, if condition is true, then it has a different chain to go. If it's false, then it has different chain to go. Similarly for while, it's checking till that condition is true, and then whatever commands are there in that while loop, it executes them, and and so on. And what So one thing that happens is that this interpreter keeps in memory what are the original values it's seeing for. So let's say my computation has something to do with some arrays or some variables, right? Now there would be some values for that variable or for this arrays index. Now it, before starting computation, it will keep track that hey, for this variable, the previous value was this, for these indexes the previous value was that. And how it uses that is that it just takes out a difference, that hey, what are the different values which got created out of this computation, and that returns back to the caller. So this is just to reduce my network call, I mean the payload size on the network call. So yeah. uh, uh, so what's next? So what I'm working right now on is that right now I have my own language. I'll maybe show you. Yeah. So this is code which is written in my language. Now you can see that it's mixture of both Python and C. So you have curly braces from C, the parentheses coming from C, but you have a def from Python. So the language syntax is a mix of C and Python. Although for anyone it's easy to write, it's not tough job, but still it's a hassle. Hey, I have code in Python, and I have to translate that. It's a hassle for any researcher or for anyone. So the first goal I have is that I want Ramanujan platform to be working with Python language, and I'm working on that. I'm very near to that, and I'm trying to commit that by mid-December 2025. Right now, it will have still the basic functionalities, so that basic codes are able to run. Then the next thing which is important to Ramanujan is that it should have something similar to CFFI support, and the reason is that all the libraries for scientific computing, they have a native code internally. For example, let it be NumPy, Pandas, or uh, 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 many such libraries, right? So the Python code in them is minimal, but the native code is enormous, and that's what gives those scientific libraries uh, uh, computation power, good computation power, right? So that's what I want with Ramanujan, that Ramanujan should support CFFIs, and so that all these scientific libraries like NumPy are supported on Ramanujan platform. And the goal for that I have is for January and 26. And then major chunks in Python language, which are OOPS and multi-threading support. For that, I'm looking for March 26. And continuously in parallel, I'll be adding more parsing logic for multiple more things multiple functionalities of Python. Now, as part of this talk, I'm inviting contributors. Right now, I'm the only contributor right now. But this project is in nascent stage, and there is a lot to learn here. So, reasons for joining. So, it's core compiler work, and there is a lot of work to do. So, it's hoops, multi-threading, locking mechanism. Then you have to add debugger support. You have to have checkpointing is something which is not there on Python, but I want that thing to be on Ramanujan. Actually, there was a support for checkpointing, but it was very slow. But I want to revamp that. So the idea is that if device crash and if it had done some kind of computing, that computing should not go waste. They should be checkpointing on that computation, and whenever a next device resume that piece of computation, it should just resume from that checkpoint. And so compiler work is the one which is very near to my heart, and it's a core compiler work. It's core computer science thing which is there. So a lot to learn there. And if for people who are interested in full stack, there is again a lot of things to work on full stack. So currently backend can kind of support thousands of parallel code request calls, and now we can have a lot of calls, and we say that, hey, I horizontally increase my machines, but that's the cost, right? So the idea is that if universities want to use it, then it has to be minimal cost. So there is where the full stack work comes into picture. uh, yeah, thank you. Any question?
Yeah, sure, Adil, go ahead.
Hi, Pranav. Thanks for presenting. I have one question and one suggestion. So, uh, right now, Python 3.13 has introduced a JIT compiler.
Mhm.
And the idea of obviously a JIT is to, instead of converting Python code to Python bytecode, you convert it to native code directly, and then whatever information is available during the execution, so you can leverage that. So is there a similar plan for Ramanujan? Are you like thinking about it? Because ultimately there will be a time, uh, considering the goals of the faster C Python project, that also was also um, supported by Microsoft for quite a long time. And I know that you also work on Microsoft, but obviously not on the same team. There are so many improvements that are going to happen within CPython. So in order for Ramanujan to stay competitive in such a landscape, it's a very daunting task. The other thing I had was a suggestion. I think this is a project that could make use of, it could benefit from grants. And in particular, because SciPy India is a community that's being sort of incubated at FOSS United, I would like to point you to the FOSS United grants. It's on this fossunited.org/grants website. And it might be something that maybe you'll find it interesting, and it applies to all speakers, so not just you. If there's any project that you have that could benefit from some money to sustain its growth in the open source space, then Force United might have something for you.
Yeah, absolutely agree. That's a great suggestion. And as far as competitiveness to C Python, so the future I foresee for Ramanujan is that it will work some complementary and supplementary to C Python, and not like a competitor. I want Ramanujan to be a friend of Python and not a competitor of that. And I'll keep taking some things out of C Python periodically. So that's the goal actually. Um, but yeah, again, some always with a mission to add something on top of what Python gives right now, but complementary and supplementary to it.
Thanks, Pranav. That is a very politically correct answer.
Oh yeah, sure. Go ahead. Yes. Guinness, you can. I think you're still unmuted.
Yes. Pranav, I have just one question. I know you have supported Python on the Ramanujan computer, but are there any plans for other languages like Rust?
Yeah, definitely. That's a possible. That's a possibility. Truly possible. So the idea is that so Ramanujan right now has nothing to do with the bytecode converted by Python. So Ramanujan has its own set of bytecode, and the interpreter runs on that bytecode. So that's a possibility that we can maintain lots of languages. For example, Rust. The idea is that we take Rust, but we convert it to our bytecode and the interpreter running that bytecode. So that's a possibility. Yes. I hope I answered your question.
Yes, thank you.
Nice.
Thanks, Pranav. So for everyone who is here, we do have a very short feedback form that if you can take like 30 seconds to fill, that would be great, because that's like we ask for ratings on these talks. So I know that we didn't have a lot of attendees, but maybe you'd like to fill it. It can help us plan the next community calls better. For example, whether this time is not appropriate for you or things like these. And all of the responses are anonymous, so we don't bite.
Yes, I think I was going to mention that as well. I think, yeah, also the links for the respective forms and also the YouTube live stream is posted on chat. Um, Thanks to all the speakers who attended. It was a great session, at least personally being an attendee. Um, Again, hope you can take out the time to just fill out the forms. It'll be really helpful for us to plan out not just the community calls like Agriya mentioned, but also the upcoming, hopefully in-person conference next year, early next year, which we plan on doing. And yes, I can. Oh, by the way, if anyone has any questions, I'll be pausing the live stream right now.